So in this lecture today we are going to discuss about motional EMF. Motional EMF. Suppose we have a magnetic field and magnetic lines of force, magnetic field lines are going inward into the board normally perpendicular to the board in this direction, and let me represent that by cross symbol. So these are magnetic field lines going into the board, and we have a rod here. This is a rod. Suppose this is a conducting rod A B. Now, if we move this one, this rod in this direction with velocity v, such that this velocity direction of its motion is perpendicular to the magnetic field. That means magnetic field lines are going into the board normally, and the rod is moving in this direction. That means it is moving perpendicular to the magnetic field. Okay. So let us assume that. So now let us also assume. Let us also assume that let us assume a complete coil. So I have assumed this one, so that this arm of this coil can be slided over these two arms. So A, B, suppose C, D. So we have assumed that this is such a coil. This rod AB, this arm can be slided over AD and BC this way. Okay. So hope you have understood. And initially its area is suppose A. Now this AB is moved towards CD with velocity v, and after time dt, suppose this rod comes to this position after time dt. This is the new position of the rod, and it covers a distance dx, suppose in time dt. And length of the rod be suppose L be the length of the rod. So let the rod AB be moving with a velocity v in the direction perpendicular to magnetic field B, as shown in the figure. We are talking about motional EMF. Now, suppose in time dt, AB covers a distance dx. Covers a distance dx. Then what will be the change in area? Now you see this is CD and this is the rod AB, and initially its area is A. Area of this surface is A. When it is moved, this is the new position, then what will be the change in area? So area of this portion will be the change in area. What will be the area of this portion, that means this portion. So this distance is dx and its length is L. We have considered that. Therefore, change in area dA is equal to L into dx, right? This is the change in area. And as you can see, in time dt, distance covered is dx. So it is moving in straight line, so distance is considered to be displacement here. So velocity v will be here dx by dt. So velocity will be dx by dt, right? So now, so as it is moving in this direction, perpendicular to the magnetic field B, which is going inward normally into the board, and this road is moving perpendicularly. So while it is coming, then it is cutting the field lines. You can assume that way. So that's why there must be a change in flux across this road, and due to that change in flux, there must be an induced EMF. So now flux is given by phi is equal to B vector, that is magnetic field. Magnetic field is a vector quantity. Vector quantity means you have you should know that vector quantity, there are two types of physical quantities, scalar and vector. Vector has both magnitude and direction. Scalar has only magnitude. Remember that. So, and A is the area vector, suppose. Now here you see, suppose this is the surface. So when you say this is a surface, this face is facing towards you, then its area vector will be towards you, which is perpendicular to the surface. Similar for this surface, this area vector, if you consider the face which is facing into on that side, not this side, that side, towards the magnetic field, towards the facing, suppose facing the board, suppose this surface is facing the board, then its area vector should be considered as in parallel direction, parallel to the magnetic field, in the same direction as magnetic field. In that case, angle between B and A, angle between B vector and A vector, theta must be equal to 0. And we know, so in mathematics, in vector chapter, you will get that if two vectors, the dot product of two vectors A dot B is A B cos theta. When we write this vector A vector, it has both magnitude and direction. And when we write this symbol without giving the arrow, that means it means only magnitude. And this is the dot product of two vectors A and B. So you will get those things in mathematics in the sector vector, and I will provide you only those informations which are used in this topic, right? Okay. So vector B dot vector A, that's going to be B A cos theta according to vector dot product, and angle between theta and magnetic field and the area vector is 0 here, and cos 0 degree is 1. That's why we can write phi. That's why we can write phi is equal to B A. So this is what magnetic flux, right? This is magnetic flux. So now we have already got that EMF, induced EMF, E is equal to rate of change of magnetic flux d phi by dt, and according to Lenz's law there should be a minus sign, right? But when you need to calculate only EMF, magnitude of EMF, this minus sign is not required there. Okay, remember that. this gives only the this comes from Lenz's law, so which explains that. Now you see, it opposes the EMF, opposes the region for which it is induced, right? That means there is induced EMF because the rod is moving in this direction. That's why, according to Lenz's law, this magnetic field will provide will apply or exert a force to oppose the motion. That means in opposite direction. So as the force acting on in opposite direction, that's why this negative sign comes. Okay. So hope you have understood that. So now minus d phi by dt. Right. Phi is dA cos theta, and cos theta, as cos theta is 0 here, cos 0 degree 1. So that is why we have got phi is BA. So let's put BA here, BA. And as we are applying a magnetic field which is uniform, okay, which is uniform magnetic field we have applied, uniform. So uniform magnetic field. So that's why this B should be a constant. So constant can be taken out, minus B dA by dt, right? dA by dt. And we have already got here dA is L into dx. Let us put here. So then what you will get? So here one more thing. So we are taking only one rectangular loop. That's why here this value of n is 1. Number of turns in the coil is 1. That's why E is equal to minus d phi by dt. Generally, the formula of EMF we used to write this way, n d phi by dt. But here value of n is equal to 1. So hope you have understood this. Now, if you replace this dA by this value, then what you will get? Minus B. So L is the length of the rod, so which is fixed. So you can write here. Then only variable is here x dx. So dx by dt. So what we have done, we have replaced this dA by this value here. So we have got this. And dx by dt is nothing but it is the velocity. Dx by dt. This one, this velocity. So that's why we can write E is equal to minus BLV. So this is the formula for EMF in a moving rod perpendicular to the magnetic field. Okay. So this is the EMF induced in this rod while it is moving across a magnetic field in the direction perpendicular to the magnetic field. So now, what if its motion is not perpendicular to the magnetic field? Now let us discuss that situation, that concept. So let me clean this here. So now here you see, let us keep this formula, we need it. Let me use the diagram. So now here you see. So this is the, suppose now let us consider the direction of magnetic field is this. This is the direction of magnetic field, B. Okay. And here is the rod, AB suppose. This is the rod. And this rod is now, this is being moved in this direction, diagonally, not along B or not perpendicular to B. Remember that. So it is neither moving in the direction of B or nor moving perpendicular to B. It is moving diagonally. Okay. This is the magnetic field, and this is the suppose perpendicular direction coming outward, and the rod is moving in this direction. So hope you have understood. Making an angle theta with B, we have assumed that. So this velocity V makes an angle theta, right? So this velocity velocity is vector quantity and it must have two components. One is in the direction of a magnetic field and one is perpendicular to the magnetic field. So here you see this is the magnetic field and this is one component which is coming out of the ball. Let me draw this way. And here the direction of the velocity is this. This is the direction of the velocity v. So let me assume that. Let us don't consider this one first. Now, so this is the theta suppose. Now it must have two components. One component along b, another component. This velocity is in this direction, in this way, and one component should be along this direction. So if you have the idea of vectors, in mathematics you must have studied about vectors. Okay. So let us find the two components. So generally this component should be v cos theta, and the perpendicular component, this component which is perpendicular to b, that should be v sin theta. Now let me explain why this is v cos theta and why this is v sin theta mathematically. Let me explain. Now you see, let me draw the diagram again. This is v and this is v, right? And this is the angle theta. Now let's make a right angle triangle here, and this is perpendicular, so p, and this is the base, suppose b. Okay, so let us find the perpendicular component, which is this component is equal to this. This is the perpendicular component of b, suppose. So let me find this one. So if we go at this one, then that one will be same as this one. Okay, so now let us find it. So this is the angle theta. Now use trigonometry. Cos theta, we know that perpendicular, sorry, not perpendicular, base by hypotenuse, base by hypotenuse. Here hypotenuse is nothing but v. So this hypotenuse is v here, velocity v, right? So in that case, so we can write v by v, right? So here v will be v into cos theta, v cos theta, right? So this component is v cos theta. This is v cos theta. Now we know sin theta is equal to perpendicular by hypotenuse. Here hypotenuse, this hypotenuse is nothing but v. So p by v, and then p will be equal to this p. This is also p. Same, both are parallel and they are of same magnitude. Assume that way. Then p will be equal to v into sin theta. So p is equal to v into sin theta. So this is the perpendicular component. This component, this is coming out of the board. Now here you see, we are not going to consider this component. To find the EMF in this rod, we are not going to consider this component of the velocity, because if the rod moves in the direction of b, this is the direction of magnetic field, suppose, and you are moving this rod along this magnetic field, then what will happen? There will be no flux change in this rod, because here you see, suppose these are two lines of magnetic field lines. These are two lines, and this is the direction. This is the direction. Here you see, if you move this way, then there will it is obvious that there will be no change in magnetic flux. To be change in magnetic flux in this rod, it must be moving in a direction which is inclined to a certain angle, inclined to these lines, or maybe perpendicular to this line, magnetic field lines. Then only it will then only there will be change in magnetic flux, and if there is change in magnetic flux, then only we will get the EMF, right? So that's why we are not going to consider this component. So the component which is only who is responsible for this change in flux is this V sin theta. Then, so if the rod is moving in this direction, this V should be replaced by this component V sin theta. Then if you replace this V, so this formula is correct for V perpendicular to B. This is correct for V perpendicular to B. But if the angle between V and B, if the angle between V and B is theta, then this V should be replaced by this V sin theta component. Then what you will get? Then in that case, E is equal to minus V sin theta into L. Let me write the L here, or you can write this L on the other side also. You can write this one, minus V sin theta into L. Right? So for this special case, the EMF should be given by this expression, and for this case we can use this formula. So hope you have understood this. Hope